maintenance. We are working currently on predictive maintenance of lubricants in wind turbine applications. And as you heard, at the heart of this kind of prediction loop, you need a digital twin. And this digital twin has to be informed either by some statistical model or maybe by some physics-based model. Remember, in offshore applications, you have 6 months in the year you can't reach your wind turbines. So a predictive model for the death of a wind turbine needs to be very good. So the question is statistical models enough to basically fulfill the needs of a wind farm? We are currently working with 2 different approaches. So we have a data-driven approach where we have a tribometer farm under similar conditions like in the wind turbine, and this creates a lot of sensor data, and we try to inform some neural network, and that leads us to a lifetime predictor. But we still don't know if that's enough. So another approach is here by assist this by a physics-based model, by multi-scale simulations. Daniele already introduced that. By combining the physics and the chemistry on different scales, we want to learn something about the wear behavior in the driver systems in the turbine to get some analytical models that might also be useful for the digital twin. One impediment for this is, of course, the structural and chemical complexity. Daniele already mentioned that too. For instance, if you have a steel surface and you look into the tribo zone of the steel surface, it's quite a complicated picture. You have a gradient in grain size, and then you have a couple of boundary layers at the outer surface, which are very complicated to describe, especially since you have a very complicated lubricant in this kind of systems where you have a base oil here, for instance, PAO. You might have some anti-wear additives, CDDP as plotted here, and a lot of other additive chemistry, which provides a lot of elements, which you can also find here in this reaction layer and as an adsorption layer. And Stuart told us something about these adsorption layers here. The problem is how much complexity you need to describe this layer and the lubricant. So do you need almost identical digital twins, or can you stick with some digital skeleton which has just a couple of basic laws with a lot of fittable parameters? And that's basically where I want to talk about today. So I don't like to stick with the complexity of a steel surface, so I switch to diamond-like carbon, because it's also used often in our days in the drivetrain of mobile systems. And diamond-like carbon is an amorphous carbon material with a high sp3 content. You can get it in hydrogen-free form, which is a TAC, and you can get it in a hydrogenated form with it's an ACH. And TAC is usually a little bit harder than ACH. Why is TAC so important? Well, in our cars, there is a trend towards low viscosity oils to save fuel. And that leads more and more into boundary lubrication. And that's why TSC coatings are important to protect the surfaces, but also because TSC has an important property that is called superlubricity. For instance, you can show by experiment and simulation that if you lubricate 2 TAC surfaces with glycerol, you get into superlubricity. And we believe that this has to do with doping of the surfaces with oxygen and hydrogen from the glycerol that catalyzes the transition to some aromatic structures that passivate both surfaces, and this leads to ultra low and super low friction. The problem with TAC is in an engine, of course, there is also steel, and you have to protect the steel. And usually you insert CDDP into the engine oil to make protective layers. Here's the CDDP molecule. And the CDDP molecule produces under shear polyphosphate films which protect the surfaces. The problem now with DLCs is some DLCs have high wear rates when they are lubricated by CDDP, and this of course causes trouble. So The first goal here was to understand the DLC wear during engine oil lubrication. And this is the main part of the talk. And then I want to discuss the implication for lifetime modeling based on what we have found for this DLC wear. So what I'm telling you now is already been published in a recent paper here about the mechanochemical wear of diamond-like carbon. And here are the co-authors, and I want to take this opportunity to thank Takuya and Gianpietro for, well, collaborating with me in the modeling of this systems, and also Valentin, Jean-Michel, and Marie-Isabelle from the LTDS for their beautiful experiments. So in Lyon, they performed experiments with a cylinder on disc tribometers, where they coated both the cylinder and disc by a DLC and looked for friction and wear. So in order to vary a little bit the different coatings, they used 5 different DLC films, ranging from a Young's modulus from 250 gigapascal to 625, and also quite a span in hardness. They included also an ACH with 20% hydrogen, and they compared 3 different TACs with small to high hardness. The roughnesses were on the nanoscale, and also the root mean square slopes were comparable, but there was also variation between 0.06 and 0.15. Now, in the tribe experiments, they found that the weak coatings, ACH and AC, gave rise to some low friction, 0.1, while all the 3 TAC coatings went into ultra lubricity around 0.02. And this was when they lubricated the whole system by PAO. Now, if you add a weight percent CDDP into the tribo contact, the 2 soft coatings behaved similarly. The soft TAC also didn't change in his tribo response, but most interestingly, the hard 2 coatings, they showed a transition from ultra low to low friction. What was more remarkable was the differences in wear. So if you look with an optical image on the cylinder and on the flat, in the PAO case, there is almost no wear. There's just a little bit smoothing during running in. But if you focus on the CDTP lubricated case, it's clear that the 2 hardest coatings, the 66 and the 78 TAC, showed severe wear. We calculated the wear volume from optical interferometry, and you see the wear is orders of magnitude higher if you lubricate hard TACs with CDTP additives. So the question was, what's going on? And of course, you can take a microscopy to get more insights into this. So they looked with SEM at all 3 coatings after the running in phase. And for the soft coatings that didn't show wear, CDDP-derived islands were observed. So the green stuff here is zinc. While for the 2 harder coatings, which had high wear, there was no zinc on the surface at all. TM and also showed that the films here are of the order of 20 nanometers for the ACH, so 5 to 10 times thinner than on steel. So that was the structure of the coatings. And the question is, what is the difference now between the soft and the hard coatings in terms of chemistry? Next step, you can perform XPS, surface chemical analysis. And we looked at all possible elements, and I just want to show you the most important element, which is the sulfur. So here are the sulfur 2p spectra. So we took the 2p electrons here and looked outside the wear scar, where you find sulfur oxygen and sulfur zinc bonds in all 5 coatings. And this has to do, of course, with the physisorption of CDDP. So here you have the sulfur zinc and the sulfur oxygen bonds. They might form by tribochemistry on the surface. Inside the wear scar, there was a pronounced difference. The sulfur oxygen bonds disappeared, and the new signal was emerging here at 164 point something, which are sulfur carbon bonds. So they are produced by sliding. And most importantly, the hard TACs here showed the highest signal in the sulfur carbon. Now you can integrate over the blue area and over the red area and create a ratio, an intensity ratio. So the intensity of the sulfur carbon bonds normalized by the sulfur zinc bonds are plotted here. And we basically compared this with a composite wear volume. And you see here that there is a strong increase in wear volume if sulfur carbon ratio goes up. So this was a hint that sulfur somehow plays a very important role in this wear behavior. And that's where we started to think and use our natural neural networks to find out what's going on here. And this is, of course, some good opportunity to practice a little bit of multi-scale simulations. So the first question we asked ourselves was, what is the effect of sulfur doping in a DLC? So how does it affect the shear stress? So throughout this talk now, I will show you results from density functional based tight binding simulation. And we produced 3 different samples, one representative for TAC, one of AC, and one of ACH, with different densities. We did some quenching protocol to produce the samples, where we also introduced a certain percentage of sulfur. And here is now the shear stress you need to drive this, this motion here as a function of the sulfur concentration. And for all 3 coatings, you see you only need a couple of % of sulfur to make the response here much weaker. So this shows that there's a pronounced weakening of the DLC matrix if you somehow manage to mix sulfur into the bulk. We did other calculations with boron, for instance. There was the response was less pronounced. So sulfur is here an extreme case of weakening dopant. So next, we wanted to ask ourselves, what are the differences in contact pressures for the 5 different coatings? They have different stiffness, so there should be something different in the contact pressures. So we performed the elastoplastic contact mechanics calculation. We took AFM data from Lyon. We fed the code of Lars Pastewka, the contact mechanics code, with Young's modulus provided by Lyon. And the load was 210 megapascal, the macroscopic load, and calculated basically the pressures inside the contact, so the microscopic pressures or atomistic pressures in the contact. And here we show the probability density of these pressures for the different coatings. So the red coatings are the hard TACs. You see that they have quite a long wing extending to quite high pressures. Now you can go ahead and calculate some mean or some median of these distributions, which we did. So here are the medians of all 5 coatings, the circles. And well, we plotted this against the quantity, which is the contact stiffness times the root mean square slope. Because in Person's contact theory, there is a relation between this quantity and the local pressure, which shows that it's not only the stiffness of the coating, it's also the topography, which of course influences here these pressure values. And this is seen, for instance, for TAC 51. TAC 51 has quite a high Young's modulus, but its pressure is smaller than that for AC. And this has to do with the very small slopes of the TAC 51. So you need both mechanical and topographical properties to understand this. So we have much higher pressure for the hard coatings, and maybe now we can explain that they somehow influence the tribochemistry of the system. So the next step is, what is the effect of local pressure on the sulfur release from the CDDP? So you can create two DLC surfaces, and then you put a CDDP molecule inside. And we did some quasi-static pressing simulations. And well, let's show what's going on. So you can press here the CDDP, you release the pressure, and then you can observe which kind of reactions you produced and which kind of products are generated here. Now, in order to understand these simulations, you have to notice two things. So with these simulations, we kind of mimic an asperity collision between two DLC asperities. So they collide, they produce some local pressure, and then they separate again. And this is reflected by this quasi-static pressing, except that we didn't take into account the shearing motion here. We will do that later. A second observation is, if you collide TAC asperities, like here, I plotted the sp3 fraction of this. By the collision, you produce sp2 tribolayers on top, and that's also seen in experiments. So a TAC on this scale is represented by an AC tribolayer. So this is why we set up the TAC as an AC. We did a couple of calculations of this sort, and you see that sometimes you can transfer the sulfur from the CDDP from the molecule to the surface. And these sulfur atoms are the most important to us because they are basically precursors for the sulfur doping. We did this for a couple of maximum pressures, which is the pressures here. And we calculated for the statistics for the number of sulfur atoms, or the transferred from the CDDP to the coatings, and the sulfur lost contact to the CDDP fragment for the ACH and the TAC. First of all, the higher the pressure, the larger the number of transferred sulfur atoms, but there is no influence of the chemistry. So ACH and TAC have, in principle, the same behavior. But interestingly, for the higher hardnesses or the higher Young's moduli, you have more transfer. That would be a hint that the harder coatings get more sulfur, which would be nice to explain the experiments. Now, we are a little bit skeptical if quasi-static pressing is just enough. So we did also quantum hemodynamic sliding simulations. Here are two examples of that, where we did the same protocol. We approached both surfaces, but then we did sliding at 300 Kelvin, and we separated that again. And again, we can calculate the number of sulfur atoms transferred to the coating. Here is the initial result, the previous result from the quasi-statics. And here's now the shearing. And you see, shearing has a big influence on this number. And in addition, also the trend with pressure almost vanishes. So the hard and the soft coating, the hard and the soft coatings get almost the same number of atoms. Here's a little bit of a difference between ACH and TAC, but I think this could also be a statistical fluctuation. These are 0.2 nanoseconds. So if you would simulate this for much longer, I would even believe that you could always release 4 sulfur atoms from the CDDP to the coatings. So this is first, it's bad news because we cannot make any difference for all the coatings for this sulfur transfer. So you get always 4 sulfur atoms from the CDDP to the coating. But there is another important observation. If you do the shearing for 5 gigapascal and below, for both type of coatings, you form a tribolayer, which is CDDP derived, and all the shearing is in this tribolayer. You increase the pressure, and then for the ACH, so for the hydrogenated carbon, there is still the tribal layer. The difference is if for 10 gigapascal for TAC, the tribal layer has disappeared. You got cold welding and chemical mixing of, or mechanical mixing of the carbon, of the sulfur into the carbon. You can specify this. So here is the sliding interface, and here is now the number density of sulfur atoms at the surface and then into the bulk. And the TAC has a quite high number density of sulfur in the bulk, while the ACH hasn't. So obviously there is a difference in the cold welding tendency between ACH and TAC. We calculate the density, the number density of covalent carbon-carbon bonds, bridging this interface here. And up to 5 gigapascal, there is not a big difference between the both coating types. But for 10 gigapascal, hydrogen leads to passivation, and without hydrogen, you get this cold welding. So this is now what we believe the final explanation, that cold welding makes here this sulfur doping. So this is the little story, quite a microscopic story of wear of these material systems. And now we can go to cartoons. So these are my summarizing cartoons. So what have we learned with this? General lessons. So the tribological boundary layer, either CDTP tribofilm or an AC doped with sulfur, determines friction and wear. So chemistry is important for kind of these microscopic models. The pressure triggers the chemical deconstruction of the CDTP, and also drives the cold welding of the asperities if there is no hydrogen in the interface. These local pressures, they depend on the topography and on the mechanical properties. And the sliding is important because it increases the reaction rates in the tribo contacts, and also it drives the mechanical mixing of the sulfur of any elements into the system. And there are additional lessons learned. We heard already from a previous talk that there is different density of lubricant molecules on the surface, and this of course is due to a competition between adsorption sites and of the different lubricants, and that influences nanorheology. So it depends on the entry of your tribo system, how much of the lubricants are here, and this of course determines the tribochemistry in the coatings. And then of course, if you have different additives, that can change the whole game. We need to understand the plastic flow behavior, because that changes the topography, and that in itself changes again the local pressures. And in real tribo systems, like in a wind turbine, you have many of these contacts, and they all talk via the lubricant with each other. So this is kind of a very complicated physics you have to take into account. So if we would go to a fully physics-based digital twin, we would need quite a big set of governing equations for the lubricant rheology, adsorption, mechanochemistry, dopant concentrations, local pressures, temperatures, plastic flow, mechanical properties, topographies. And I agree with Daniele that this would be some work which we would extend for the next 2 decades. But of course, we could say, don't take a full digital twin or full model. Let's take some kind of a skeleton of a model. And this is a model which has been formulated by Ida Turing and his co-worker. And I think it would also apply to our DLC contacts in the case that the pressures, the local pressures, are smaller than 5 GPa. So Ida did contact mechanics. He got the local pressures. And these local pressures are fed into a growth model for the tribofilm height, which has a mechanochemical growth term and some empirical wear term. And here there are a couple of parameters pop up, like activation energies, activation volumes, or some wear rates, which need some fitting. And you could hope that if you fit this, it might also work in some wind park, maybe. In our case, we have to extend this model by the pressures larger than 5 gigapascal if you have a TAC coating. And this could mean that you, in this case, the tribofilm formation stops, and you could use some R-shot wear model to predict the wear in the DLC coating with some wear coefficient. But with this kind of reduced models, you always have the problem to fit all these quantities. And maybe there the machine learning could step in. So for instance, you could do some estimate the R-shot coefficient in this model by doing some high throughput quantum mechanical calculation of the shear stress in the DLC as a function of doping concentration, as it has been done here for these 5 elements. And in combination with some tribometer farm or something, you could have a machine learned R-shot coefficient as a function of the dopants. But of course, how to get the dopants and so on. So the censoring is kind of a difficult task here. Last slide, an alternative benefit from the multi-scale simulations. Well, at least you get some basic understanding which quantities are crucial and influences the wear rate. And one quantity we found is the nanoscale slopes. Of course, you can measure in experiments in situ the topography of the driver surface, for instance, using digital holography. This has been done by Martel Dienwiebel, and these are basically his slide. And from that, of course, you get the slopes on the nanoscale. And maybe these are very good quantities to fit into a neural network and to predict. So the question is, which kind of sensor signals are you really need? Acoustics for itself is not enough. You need some information about topographies and chemistry. And maybe that's the main benefit from the simulations. All right. Thank you for your attention. And I have to thank for a lot of funding and computer time here in Germany.